We usually write out numerical sequences as flat, left-to-right strings of characters. But forcing complex mathematical relationships into a single dimension strips away their actual architecture. Look at this output of a 30th degree polynomial expansion. Trying to parse higher-order patterns from this massive block of raw text is incredibly inefficient. The limitation goes all the way down to basic arithmetic. Even a simple calculation contains hidden, multi-dimensional branching structures that a flat line of digits completely ignores. This diagram shows the matrix for multiplying 1234 by 567. We see how the numbers break apart and recombine into a compositional network. Following these pink downward paths and light blue curved arrows makes it obvious these operations form a directed, two-dimensional graph. In 2026, Umair Abbas proposed a theoretical solution to this mapping problem. He argued that we have to stop treating numerical sequences as flat character strings altogether. His thesis states that number patterns are actually spatial linguistic expressions. To understand them fully, they must be encoded as layered topological objects. By lifting data out of a one-dimensional format and onto a geometric manifold, we expose the underlying compositional architecture. We give our systems the ability to detect higher-order semantics that a linear parser is guaranteed to miss. To build this spatial grammar, we have to throw out the traditional alphabet of sequence tokens and replace it with a geometric lexicon. This graph demonstrates a flip mechanism. It translates sequence variations into spatial locations, like the origin and nodes 1 and 2. Tracing the green paths proves a crucial point. A combinatorial change mathematically equates to physical movement across the map. When the sequence data grows more complex, with hundreds or thousands of interdependent variables, this flat map folds upward. It extrudes into a three-dimensional generalized permutohedron. This specific polyhedron acts as the structural container for highly complex categorical distributions. We can now define the allowable combinatorial changes by mapping sequence transitions directly onto the faces and vertices of this geometry. The rigidity of the polyhedral structure forces the sequence to obey the strict compositional rules of category theory. By locking sequence transitions to the physical edges of the polyhedron, any movement across the shape follows a predefined, mathematically valid path. The structure itself acts as a container that enforces logical consistency during data transformation. With the vocabulary set, we need rules for syntax. Standard spatial grids rely on periodic repetition, but repeating grids fail to capture the recursive, branching complexity of actual numerical data. If you lock a sequence into a repeating geometric grid, you force it into an artificial infinite loop, and it loses its distinct linguistic value. This image shows a 2023 mathematical discovery that solves the problem, the aperiodic monotile, or Einstein shape. By looking closely at the vertices and edges of this central cluster, we can see how individual hat shapes interlock to build a larger, continuous metatile. These metatiles are governed by strict mathematical substitution rules. Every piece forces the system into a pattern of organized, hierarchical growth. This yields a remarkable property. The tiles will cover a plane to infinity, yet the overall structure will never form a periodic repeating pattern. Applying this to numerical data gives us our syntax. The monotile provides a physical model for linguistic structures that are mathematically lawful but entirely non-repeating. Using an aperiodic foundation guarantees that an encoded sequence can exhibit self-similar fractal expansion across multiple scales, while completely avoiding the trap of a degenerate periodic loop. Mapping the sequence is only the first step. Data is dynamic, and our geometric syntax needs a mechanism to evolve. To drive this grammatical evolution across the manifold, Abbas introduces the logic of cellular automata. This image illustrates an initial state. The evolution of the sequence starts right here, as a strictly localized update rule between adjacent cells. When you execute that local rule repeatedly, the entire grid transforms. This diagram shows a 4x5 taxonomy of 20 distinct stabilized sequence variations. Notice how a minuscule change in the starting input parameters results in a radically different final morphology. This visualization reveals what happens when these topological rules are run continuously across a massive dataset. The sequence is not following a top-down master equation. It evolves organically from the bottom up, determined strictly by how individual nodes interact with their topological neighbors on the graph. We now have the complete theoretical pipeline, a polyhedral lexicon, aperiodic syntax, and cellular automata driving the dynamics. When integrated, these three pillars form a fully realized spatiolinguistic manifold. The data comes alive as a shifting, crystalline geometry. The immediate computational advantage of this framework is its filtering capability. It mathematically separates stable geometric patterns from raw structural noise. This framework identifies anomalies by monitoring the physical continuity of the manifold. In this system, an incorrect value creates a jagged vertex that violates the manifold's continuity. The anomaly manifests as a literal structural break in the geometry. Abbas proposes a direct evaluation pipeline. A system first identifies the raw sequence pattern, then categorizes its geometric form into a specific compositional class. Mapping an anomaly to a specific compositional class reveals its predictive branch. By isolating the exact structural break, the system can determine the limited set of logical paths the sequence is capable of following next. Mapping data onto a categorical geometric language allows sequence classification to be treated as a problem of spatial computing. This theoretical proposal suggests that numerical structure is not just a string,